Welcome to lecture 26 of Machine Learning from Data. We're going to continue discussing the kernel trick and look at some results on data and discuss a little bit, how to pick the kernel and what exactly is the kernel. Okay, but let's have a quick recap of what we did before. So we continued discussing the support vector machine, but we now introduced the nonlinear transform, and in particular, we introduced the dual version of the problem. Okay, and what was the reason that we did that? The reason we introduced the dual version of the problem is it allowed us to implement the entire support vector algorithm, the entire optimal hyperplane algorithm, using just inner products. Okay, and what was that? And it turns out that just like the original primal version of the support vector algorithm, the optimal hyperplane algorithm, the dual version is also just a quadratic program. Okay, and I'm showing that quadratic program boxed here on the top right. Okay, and the version here that's being shown is the version that can be used with non-separable data. Okay, so C is this regularization constant that trades off the margin violations with the size of the margin. Okay, and you get to pick C. The larger C is, the more you're focusing on the in-sample error, the less you're allowing margin violations. The smaller C is, the more regularized the classifier will be. Okay, now, as I mentioned, this dual version of the problem allows us to formulate the entire algorithm, including the final hypothesis as shown on the bottom left, entirely using inner products. Okay, and that allowed us to say, well, what if I could compute the inner product in my feature transform space without actually going there? And the object that does that inner product computation is what we call a kernel. Okay, so let's see what we were able to accomplish with the support vector machine. So first, the optimal hyperplane controls overfitting. Why? Because it's maximally regularized. It has the largest possible margin, the largest robustness to input noise. Okay. And this is illustrated, with a feature transform into the third order polynomial feature space where, if you just do regression for classification, you clearly overfit. But if you do the optimal hyperplane in this third order polynomial space, then, things look good. And that's because the complex dimensionality of the space cannot be fully utilized because the algorithm maximally regularizes, and what effectively defines the separator is this small number of support vectors. So effectively, the number of parameters, the few support vectors that you can use to define the boundary is small, even though you have many dimensions to play with. Okay, and this suggests we can go to large dimensions. We can go to almost perhaps infinite dimensions while not losing control of E out, because we are in some sense optimally, maximally regularized. And it's a very nice algorithm because it's not iterative, it's a quadratic programming algorithm which we know how to solve. And last lecture, we addressed the computation issue. That's what the kernel allows us to do, because going to infinite dimensions is not physically possible, it's computationally impossible. Okay? But the kernel allows us to do that by saying, we can by exploiting the fact that this algorithm is an inner product algorithm and saying that we can compute that inner product using a function in my original space. That's what the kernel is. Okay? And we did a few examples, and we'll see a few more examples today. Okay? So we saw the polynomial kernel last time, where if your feature transform takes you from your original X space x1 to xd into a polynomial space, okay, and we played around with algebraic constants to make things more convenient, okay, then we saw that we can compute the kernel in our original space, okay, by just taking the dot product in our original space and raising it to some power, okay. For the quadratic polynomial kernel, we raise to the power 2, and the general qth order kernel raises to the power q. Okay, now, even though this is not an infinite dimensional transform, it's very efficient to compute the kernel in your X space, but transforming to a high order polynomial space and then computing the dot product in that space is computationally challenging, especially when Q is large. And so immediately we get the benefit of the kernel just even in finite dimensional polynomial transforms by virtue of the fact that the kernel computation in our original space is quick. Okay. And also it doesn't entail us having to even construct the nonlinear features. We only need the inner products. Then we discussed the Gaussian kernel, which is also called the radial basis function kernel, and we'll see why in a little while. Okay. And I explicitly derived the one-dimensional RBF kernel, which corresponds in some sense to a transform into an infinite dimensional, sort of almost like a polynomial infinite dimensional transform, except for the fact that you normalize by e to the minus x squared. And we derive the kernel. It's e to the minus, the difference between x and x prime squared. So that's basically the Gaussian. Okay. And there's the d-dimensional version of the Gaussian kernel, which we also mentioned last time, e to the minus gamma x minus x prime, the norm of that squared. Okay. And I'm showing on the right a few examples of fitting the digits data with different choices for gamma and different choices for C. Remember the soft margin. Okay, C large means you're basically the hard margin. C small, basically you're focusing on regularization, not so much on fitting the data. Okay, allowing lots of margin penetration. Okay. Now, gamma is an interesting guy. We previously saw the Gaussian with an R squared in the denominator. So gamma plays the role of the inverse of the scale. So gamma large means that the scale is very small. Gamma small means that the scale is very large. Okay. And so what I'm showing here is, on the top right, C is infinity basically means C very, very large means you're doing the hard margin. Okay, in this infinite dimensional space. Now you can get away with that because we know the data is separable in this infinite dimensional space, and so you can run the hard margin classifier. And look, no surprise, you have fit the data perfectly. Okay, and you have clearly overfit. So choosing when you have an infinite dimensional kernel, you're doing learning in an infinite dimensional space. You cannot go for the hard margin classifier. So you have to go for the soft margin classifier. And we've picked now for the bottom two pictures C reasonably small. Okay, which means that you're focusing more on regularization, much less on the sum of the margin violations. Okay, so C is small. Okay, so that means C small means focus less on the in-sample error. Okay, and now gamma in the middle picture, the width is very small, so you get a very wiggly boundary. Okay, but you can see some margin violations. And even some misclassification. So you see this red X point here, it's in the blue region, and these blue points are in the red region. So that's coming from the fact that we are allowing margin violations. C is not very large. Okay. And what happens if you choose gamma small, so you choose a larger radius? Well, then it's equivalent in some sense to the kernel, not having very, very narrow bumps, but much wider bumps. Okay. And now you see you get a beautiful separator. Okay. Something like close to the best we've seen so far. Okay. So awesome power that has come now with the ability to use a kernel to do learning in infinite dimensions. You have to regularize, so you have to pick C small. Okay. And you have to choose your kernel width carefully. So let's see what happens with different kernel widths gamma. Okay. So as you can see here, when gamma is small, that means that the scale parameter is large. Think of this as Gaussian bumps that are large, similar to an RBF kernel. And we'll see why we should think of it that way. And you get a nice smooth classifier. And if we would identify the support vectors, there would be these few red and blue data points that are close to the curve. So a nice smooth classifier that seems to do a good job. If you choose a medium gamma, so small width kernels, okay, you're starting to get more contorted regions that are placing small bumps at the data points. And if you choose gamma very, very large, so tiny scale parameter, it's basically starting to look very close to the nearest neighbor. So and you'll always fit the data. Okay. So the RBF kernel is very powerful. It's a transform into an infinite dimensional space, and you basically have two parameters to play with. You've got the amount of regularization, which is, you should pick that to be reasonably small, so that because you're in infinite dimensions, you need to really focus on regularizing, not so much on margin violations, and the width of the kernel. The width of the kernel, because we don't know, we're not ever physically going to transform into this space, we don't know what the right scale parameter there is. So the gamma and the C often have to be chosen using some technique like cross-validation. Okay. So now, let's dig a little bit deeper and see a few more kernels. I'll show you we'll look a little bit more closely at this RBF Gaussian kernel, and I'll show you a kernel for neural networks, and then we'll sort of try to understand what exactly is the kernel measuring. This is what it's going to turn out, is going to bring us all the way back to similarity-based methods. And then we'll talk a little bit about how do you pick your kernel, and I'll show you some results, and that'll end today's lecture. Okay, so let's go to the board, and then we'll come back to see some pictures, nice pictures.